A second option for us besides solving quadratic equations by factoring is to use square roots. But before we can use square roots, we have to make sure that we can simplify radicals like the ones that are in front of us, because not all solutions to quadratic equations are integer values. Sometimes we just have a square root in our answer, but we need to simplify those square roots. So we take a look at square root of 24. The rule for any problem like this is a number like this is we have to make sure there are no perfect squares left underneath the radical. And so what we do is we engage in some factor tree work. And what we're looking for is either pairs of numbers or perfect squares that are trapped underneath the square root symbol that we'll be able to take the square root of and then take those to the outside of the square root symbol. And then sometimes we'll have stuff left inside. So obviously square root of 24 is not a perfect square, so there's going to be something left underneath the square root symbol when we're done. So we could factor tree this any of a number of ways, but I'm going to opt for 4 times 6. I'm always going to try to factor it into something that involves a perfect square. Like I see here, because 4 is a perfect square, I can take the square root of that. So the square root of 4 is 2. So instead of having a 4 underneath the square root symbol, I now have a 2 on the outside. Now this 6 here, I could continue to factor tree it down, but it's only going to factor tree as far as 3 times 2. That doesn't really lead me anywhere, so I could have just stopped at that 4 times 6, and so that 6 is trapped underneath the square root symbol, and so I'm going to leave it there, and so now this is a simplified form of the square root of 24. If we jump to the second example, square root of 54, again, we've got to recognize that it's not a perfect square, but we have to look to see if there are any perfect squares inside of it. So with 54, again, we can factor tree it many different ways, but I'm going to go with 9 times 6. Could have done 27 times 2. But 9 times 6 I like because, again, 9 is a perfect square. So I'm going to be able to take the square root of that. So the square root of 9 is 3. So I'm going to have a 3 outside the square root symbol. And once again, we can see that 6. I'm not going to bother to factor tree it because it doesn't lead anywhere. So my answer is 3 times the square root of 6. For the third example in this set, I've got 125. Again, not a perfect square, so I start my factor tree work. So I know 5 divides evenly into it. If you need to use a calculator to help with some of this factorization, feel free to do so. But I know that 5 times 25 equals 125. So 5, I can't do anything with that. But 25 is a perfect square, so I'm going to take the square root of 25. That comes out as a 5, and then I've got a square root of 5 because of this 5 right here still trapped underneath the square root symbol. So 5 root 5. Jumping to the bottom row, square root of 72. So for this one, we could say break it into 9 times 8, right? There are plenty of options as to how we could have broken this up, but if we go with 9 times 8, I see that I have a perfect square here in the 9, so I'm going to be able to take that out, and I'm going to have a 3. But then I've got this 8 that I have to continue to factor tree down. And so I've got 2 times 4, so the 2 doesn't lead me anywhere, but the 4 is a perfect square, so I'm going to take that out, so the square root of 4 is 2, so I've got 3 times 2, and then I still have this 2 left here, so I've got a square root of 2 still trapped underneath the square root symbol. And so the last thing I'll do is I'll multiply 3 times 2, that'll give me 6, and then I still have the square root of 2, so I've got 6 root 2 as my result. I do want to demonstrate one thing about this simplification. So if we go back to the square root of 72, let's say that we had factor treated a little differently. So instead of going 9 times 8 and immediately getting that perfect square of 9, let's say that we had done 3 times 24. And then, so I don't have a perfect square here, so I factor tree again, and so I go 3 times 8. Then the 3 is finished, so I can factor tree that 8, so I get 4 times 2. So I can see that 4, I'm going to be able to take that out, and there's my 2 that I took out earlier. But I'm not ending up with the 9 when I factor treed the 72. The other thing that we can look for, instead of perfect squares, are pairs of numbers in our factor trees. Because if we were to remultiply that 3 times 3, it would be 9, which we could take the square root of. So if I have a pair of numbers in my factor tree, it comes out as a single of that number on the outside. So in this case, I can kind of consider that square root of 9 taken out as a 3. I've got this square root of 4 taken out as a 2, and then I'm still left with this 2 here. So I'm still ending up with the same circumstances as I did when I factor treat it into 9 times 8. But sometimes we just don't stumble into the perfect square depending on how we go through our factorization. And so we just need to recognize that this circumstance here of having a pair of numbers underneath the square root symbol is the same as having a perfect square. In the last two examples, the situation that we have is a square root in the denominator of an expression. And so one rule for an expression to be simplified is that we cannot have any square roots in the denominator. So hopefully from our Algebra 1 days we remember that we can simplify this, we can deal with this circumstance by multiplying the top and bottom by whatever is underneath the square root symbol in that denominator. So I'm going to multiply the top and bottom by the square root of 6. By multiplying the top and bottom by the same thing, I'm not changing the value of my fraction. It's still the same number as it was before. It's just going to look different. And so up in the top, I just have 1 times the square root of 6, which is just the square root of 6. And then on the bottom, I have the square root of 6 times the square root of 6, which is the square root of 36, which I can take the square root of, and so it just turns into 6. So by multiplying root 6 times itself, I basically just cancel out that square root symbol. And that's the same principle that we used over here for this idea where a pair of numbers underneath the square root symbol is just like having a perfect square. So here, root 6 times root 6 gives us just a 6. And now we're tempted to reduce this fraction since I've got this 6 in the top and 6 in the bottom, and we think, oh, we could just reduce those. But we have to resist that temptation because that 6 that we see in the numerator is not really a 6. It is a square root of 6, which is something in the neighborhood of like 2.5 if you were to push buttons on your calculator. So this is as simplified as we're going to be able to get. In the second example, we'll do the same thing. We'll go ahead and multiply the top and bottom by what we see underneath the square root symbol in the denominator, so square root of 18. So in the denominator, that means I have 18. And then in the numerator, 1 times square root of 18 is just square root of 18. But this time, the square root that I have in the numerator has a perfect square inside of it. I can simplify this. And so I can break square root of 18. Again, there's a couple ways I could do it, but let's say we broke it up into 3 times 6. I don't see any perfect squares there, but if I factor tree this 6 here, I can break it into 3 times 2, and so here we've got this pair of 3's underneath the square root symbol, so I'm going to be able to take that 3 out, so I've got 3 on the outside. This 2 is still trapped underneath the square root symbol, so I'm going to have a root 2. And then I still have the 18 in the denominator. And now, unlike the previous question, I can reduce this fraction. Because whereas on this one right here, the 6 in the numerator wasn't really a 6, it was trapped underneath the square root symbol. In this second scenario, I have a 3 that's on the outside of the square root symbol. So that 3 and that 18 can reduce. So I divide the top and bottom by 3, so this 3 turns into a 1. And then 18 divided by 3 is 6. And so our ultimate result on this one, we just have 1 times root 2, or root 2 in the top, over 6. And again, because that 2 up in the numerator isn't really a 2, it's under a square root symbol, I can't reduce the 2 and the 6. I'm stuck.